So today we'll be talking basically about Turing machines, simulation, and in some sense, I like this phrase that's used in Aurora Barak, and why the computational model does not matter. And so we are trying to understand sort of the power of algorithms and what are the resources that a particular problem needs. And the problem is when you start getting into formal definitions, you have to specify your model of computation, and then it starts appearing that the resources will depend on the computational model. And that then doesn't allow for a nice theory. So you'll see that we'll be making certain choices which will help us build a theory that is in some sense independent of the specific computational model at hand. And so recall, a Turing machine, is a sort of structure with a tape and a head and states. Now, conventionally, we don't think of algorithms in this way. So part of the issue is that in Turing's time, they did not have computers. So they were building all of these foundations and they came up with machines like this, which were convenient to represent an algorithm. We don't think of algorithms in terms of states and tape and movement of a head. On the other hand, what we'll see is that representation in this form is convenient for many proofs. And so what I want to discuss today is basically how you can convert whatever model you have into a model that looks like this. Okay, so the way that I am going to talk about Turing machines is not to have a state machine, but instead I'm going to replace this by a procedure here, right? Which is going to be some fixed set of instructions. And so we can sort of switch between these. Instead of thinking of it as states and transitions and defining a transition function, in my descriptions, I'm going to use a procedure, which we write as pseudocode. But, of course, I'm going to assume that there is a tape and there is something being read. So what I will explain is, I will describe something which can be converted into moves of the heads. Okay? So this is the way that we're going to sort of talk about Turing machines. Now, sort of given this description, I sort of want to go back to the question that I had asked. And the question that I had asked was, suppose a Turing machine, let's consider a new kind of Turing machine that has a register that contains a natural number. Okay, so when it transitions, the Turing machine can increment or decrement the register. And the Turing machine's function depends on the register value, meaning that if you look at the Turing machine transition function, it is going to be of the form q times n times sigma. Okay, this is what the transition function looks like. And then, of course, based on this, it's going to go to some q prime, it's going to write some sigma prime, and then maybe it goes left or right or whatever have you. And the question was, can such a Turing machine be simulated by a standard Turing machine? Okay, so answers, any thoughts?
One way you could possibly do it is have another tape that kind of that acts as a register, and we already know that multiple tapes is equivalent.
Okay. But then how do you simulate the transition?
You have like a dummy transition that kind of reads through what goes on, reads the the content of the other tape, the register, the number, and then accordingly you make your other transition. So there's like one or two transitions that you would have to do in between each transition.
You have to be careful because the transition function depends on the register content, which is a natural number, and the state. So it depends on the state and the register content. Based on this, the Turing machine is going to make some action. How can the standard Turing machine know what the register value is? It can read it in this other tape one by one. Now it has a head that is going to be reading it.
What if, so in our transition function, we have the state and the tape alphabet, we have that, and then that transitions to another state where we do a full read of that.
Read, okay, sure.
We have the number and then again come back.
You don't have the number. You read it, but you can't store the number in a state.
Okay.
You're right that you can read the number, but you cannot store all of that into a state. The transition function that you finally give can only depend on Q, which is the state, cross, okay, so in this case there's no, that's not there, but times sigma. So you have, the right thought, but there's a twist. So you have the right ideas in how you would approach this. But anyone else have someone who has not talked to me about this problem? So the answer is actually no. This is not possible. I'm going to sketch out the answer, but the formal proof of this, I will give this as part of, as one of the homework problems, just to sort of get warmed up. The answer is no, because, so let me just going to move this paper out of the way. And the answer is no, because, sorry, let me zoom out a bit. Can all of you still read this? Yes? Okay. The answer is no, because such a Turing machine can compute uncomputable functions. What if delta, the transition function, is itself uncomputable? Then such a Turing machine could definitely compute the value of delta. A Turing machine that has a register with the natural number such that the transition function depends on the register value can essentially compute all possible functions, all possible Boolean functions. But we just discussed earlier that there are uncomputable functions. The catch here is that the description of this transition function is potentially infinite. I never said that this has to be finite. The definition just says that for any, you can choose whatever transition function you want. So such a Turing machine can compute uncomputable functions, which is not possible. We know that by definition, a standard Turing machine only computes computable functions. Okay, does that make sense?
Could you repeat that? Sorry.
So what is the definition of this machine? This definition of this machine, to define this machine, you specify a delta, and then you specify the states, you specify the alphabet, you specify the start and end states, and you specify delta. I never said that the delta has to have a finite specification. So delta could be an uncomputable function. But if the Turing machine can definitely compute the uncomputable function if it has it as part of its transition input, because it could read its input, store that input into the register just by incrementing or decrementing. It could store the input into the register and then just decide an uncomputable function. Right? So therefore this is not possible, and this is going to be your first homework problem, so please make sure you understand it, because I want you to write this argument out formally. Questions? Is that clear? Okay, now I'm going to give you another question of this form, and this is also going to be a homework problem. Question, and again, it's the same setting. So the Turing machine has, okay, so this is a consider a Turing machine that has a register that contains a natural number, contains an element in n. The register can increment or decrement, at each transition. The transition function can depend, so the transition function can depend on whether the register has value 1. So that's what, so think of it as a transition function depends on Q cross sigma, whatever is being read in the head. Technically I should put, whatever, sigma union space, times a Boolean 0, 1, and this is simply does register have the value 1, or is register 1. Can this be simulated by a standard Turing machine? The answer is yes. And this is going to be a homework problem, and I want you to figure this out. I will, when I write down the homework, I will of course write this down formally, and give you the PDF. But these are the two questions that I want you to work on. So the first question, I've given you the answer, and I've told you what the answer is. So I want you to write it out formally. And for this question, again, I'm telling you what the answer is, but I'm not telling you how to prove it. Are there any sort of questions about the question? Like, don't tell me what the answer is, but do you have any doubts about what the question is asking, or what the difference between these questions are? I'll try to put them up side by side if I can, or somewhat scrunched on space. Yes? All right. So actually there was a bit of a digression. I want to go back to why the computational model does not matter. So a standard Turing machine a standard Turing machine has a single tape, and has basically the binary alphabet. Right? That's what a standard Turing machine is. Now, what we will discuss is what happens when you consider other variants of Turing machines. So, before we get into that, let's first define, and just so that we're sort of all on the same page. So let f be a function from 0, 1 star to 0, 1, and t be a function from n to n. And actually, this could even be 0, 1 to the star. And we'll say a Turing machine M computes f in, we'll say, t of n time. So we're going to use this notation. A Turing machine M computes f in t of n time if the following holds. So firstly, for all inputs x, m of x is f of x. And secondly, for all x such that x is n, so for all inputs of length n, the number of operations performed by m on input x is at most t of n. So this is just sort of writing out formally what I mean by computing something in a particular runtime, right? This is just so that we all are on the same page over here. So does this make sense?
Quick question.
Yes.
In the normal, or to my recollection, the normal standard Turing machine only outputs accepts or
rejects, right? But you could imagine that. You could imagine that whatever is the content of the tape at the time of halting is the output.
Okay.
That's why I said you could have the star, you could not. And I'm just giving the more general definition because in case later on in the course we come up with actually computing functions, then we have this definition. But you're right. The standard definition would not have the star, it would just be whether it accepts or rejects.
Okay.
Right? So of course this by definition says that the Turing machine has to halt on all inputs. Right? This is imposing the fact that it has to halt on all inputs. So we're talking about recursive functions, if or decidable. We're talking about decidable functions, not recursive. Sorry, decidable functions. Okay. Any questions about this? This is likely a standard definition that you may have seen in the past. So now here is the challenge when you want to build a theory of computation. So now let's go back to, let's think of languages, right? So we can also think of F, or we can think of M computing, or probably the better word is deciding a language L in t of n time. So the natural question that one asks in sort of computational complexity is, given L, what is the most efficient M? or given L, how small can T of n be? Does that make sense? So this would be like the natural question that you have. What is the best possible algorithm? So how small can you make the running time? Which is also saying what is the most efficient. And I should say technically it's time efficient. Okay? Any questions?
What exactly do we mean by small? Or how do you compare?
Let's say asymptotically.
Okay.
Let's say what is the asymptotically smallest, right? You're right that this is don't take this as a formal question. Think of this as an informal question. The challenge with these sorts of questions is that you could potentially decrease the running time by increasing the number of tapes or increasing the alphabet size. So it seems like you could cheat. Does that make sense? So for the same problem, you could compute it more and more efficiently using a Turing machine that uses more and more tapes. And so the question then is like, does this even make sense? If you could make this arbitrarily smaller and smaller using a more and more complicated Turing machine, how would we even build some theory? And towards that, what we need to do is to argue that we can put a standard Turing machine here and we'll still have, we can still say something reasonable. So maybe let me start explaining. Let me give more clarification of what I mean here. So the first claim that I want to make is, suppose f is computable in time t of n by a Turing machine M with alphabet sigma. Then f is computable in time t of n by a Turing machine. Is computable by a Turing machine with the binary alphabet in time c log base 2 of sigma times t of n, where c is a constant depending on m. Okay, this is not a difficult theorem to prove, but I want you to just understand it. What this says is, suppose you wanted to compute some function. So remember, we agreed that the alphabet for the functions is just going to be binary. We're just looking at binary encodings of the input and the output. On the other hand, the Turing machine itself might use a more complex alphabet. The Turing machine could use a more complex alphabet. But what we're saying is, if f is computable by a Turing machine with a more complex alphabet, it is also computable by a Turing machine with the binary alphabet, but you pay an extra factor in the running time. Okay, does this make sense? So does the statement make sense? Questions?
And I would imagine the way that you would do this is just by essentially having enough slots to have the 0, 1, 1, like as a binary encoding of your alphabet.
Exactly. You could just use a binary encoding of your alphabet. Precisely.
And you have to just spend a few extra steps to basically read out an entire symbol.
Exactly. So you have to read out an entire symbol. You have to store it in the state. Right? You could store that in the state, and then you could basically then run whatever transition function was there earlier on this new machine. Okay, so I can discuss this a little bit more, but questions, please. Actually, now I even have polling set up. So let me just click on the polling, and I mean it's just a generic question with 4 options: A, B, C, and D. And so what I want to ask is, and it's anonymous, so you can go ahead and answer. The question is, do you see the proof of this? And A for yes, and B for I'm not sure. So let me just go ahead and launch this. Do you see it all?
Yeah, I can see it.
Now what I need to figure out is how do I actually see the answer? Oh, there. Good. Okay, I see the answer. So about 5 people have responded. So the more that you respond, the more that I can actually, adapt things to cover and make sure that you understand what's going on. So so sort of help me out here.
What were the options again?
A is yes, I see how to prove this, and B is no, I do not see how to prove this. Okay, so I guess now I have enough information. 10 people have answered, so it's 50-50. So let me go ahead and let me sketch out the proof over here. Okay, so let me give the proof. All right, so I'm just going to end this poll here. So the proof, as was just mentioned, is binary encoding. Binary encoding. Okay. So what we can do is let us define some encoding function, encoding phi that goes from sigma to and we'll just keep it a little bit safe. We'll encode it by 0, 1 to the log base 2 sigma. So we have some sort of encoding where now each symbol is encoded exactly in these many bits. Okay. So now let me now describe what the Turing machine is going to do. Okay. So the first step is the Turing machine is going to do, so this new Turing machine, this is the standard Turing machine that is going to perform this. So it's going to do an initialization. So remember, the input is in 0, 1 star. And so what can be done here is that the head goes over each symbol. The head goes over each symbol, right? And replaces over each symbol sigma and replaces it by phi of sigma, shifting left to give enough space for the next encoding. Right? So all I'm saying is here's what it's, so initially the input is going to have 0, 1, 1, 0, so on and so forth. And so the Turing machine is going to first read this. it's going to replace this by a log n bit encoding of 0. Remember, 0 itself is sort of going to be encoded. Right? So we can think of sigma contains 0, 1, and a bunch of other symbols. So think of it as an ASCII encoding. So the ASCII encoding of the number 0 is not just 0, right? It's some 8-bit encoding. So it's going to go and it's going to put the encoding over here. So it's going to move that sort of to the left. So it's going to put sigma of 0. It's going to leave, it's going to leave log base 2 sigma. I'm just going to refer to this as k. So it's going to leave k bits empty here, k slots empty here, and then it has this. Then the head is going to read this. It's going to convert that to phi of 1, right? And it's going to sort of write things here. So, so one has to do this a little carefully. One has to do this a little carefully. Because if you think about it, you might be worried about sort of having to shift everything all the time. So what the Turing machine can do is it can sort of read the next log base 2, that's read the next k symbols, sort of store this in the state. Right, so it can store the symbols in the state because there are only these many symbols. So it stores it in the state, and it would, so that whenever it writes, it can always remember, what it has moved over, and it can sort of do this more carefully. Okay. Does this make sense? So it can basically, it's sort of the head is going to go through this thing, and it's going to actually sort of like re-encode every part of the input. It needs to be done a little carefully. So is this sort of clear? And if you want to even simplify it more, then let's just say it is computable by a Turing machine with 2 tapes. If you needed the extra tape, so you could then sort of write everything on the extra tape. So this is sort of the initialization step. Then at each step, the TM reads k symbols, stores it in the state. Right? So it reads k symbols, stores it in the state, and so it has the state. The state will store what the head is reading, right? So the previous Turing machine was reading a symbol in sigma. Now it has to read k symbols to know what to transition, and then sort of it applies the transition function of the original TM. Right? So this is basically a simulation. This is a very important concept. So this is how you would simulate the Turing machine. So any questions about that? Any questions? This is how you would simulate. Now what is important to note is that one step of the old TM becomes equivalent to k steps of the new TM. right? Because to do one transition, the Turing machine has to read k symbols. And so if the running time of the old, by the way, the old Turing machine, I mean this Turing machine, the original M, right? This is the original M. So if the running time of the old TM, which I called M, was t of n, then the running time of the new Turing machine is k times t of n, right? Which was exactly this sort of log base 2 of sigma. And that's the proof.
But wouldn't you need k steps to read the symbol and then k more steps to write a new symbol?
So I should say you're right. So it's ck for subconstant. You're right. So it would be 2 times that, and maybe potentially more because you're storing things in the state. So you're right. It could be 2 times that. So it's some constant times k. In this case, the constant could just be 2. Any questions, please stop and ask me, because we're going to be doing lots of simulation arguments now.
Just a
Now we're going to do a much more sophisticated simulation argument. I sort of hinted at it last time. Let me do it again this time with a slightly different argument. And here's my claim. So I'm going to say if f is computable by a, I'll say 0-1 alphabet Turing machine M using k-tapes. Okay, so it's a 0-1 alphabet using k-tapes. Then f is computable. By 0-1 Turing machine using k-tapes in time t of n, right? So there's a t of n over here. Then f is computable by a standard tm in essentially in c k t of n squared time. This is important. So what I'm saying is, suppose you have a Turing machine that uses k-tapes and computes in time t of n, then you can use a standard. So standard is, so what do I mean by standard? Standard is binary single tape, right? The vanilla Turing machine. So you lose a square factor, but it's the same square for any k, right? C times k times t of n squared. And c is some constant. C is a constant here. Okay? Now this is not a very difficult argument. We discussed it last time, but I'd like to do it again. And I'd like to keep track of the running time. So the proof is we interleave the k tapes into one tape. And typically you can imagine if it's a k-tape Turing machine, the input might just be on one of the tapes. Okay, the input might just be on one of the tapes. So what does interleaving mean? So if you have k tapes here, we'll construct a single tape over here. So this is tape 1, tape 2, and tape 3. So we'll say this is tape 1, this is tape 2, this is tape 3, this is tape 1, tape 2, tape 3, so on and so forth. So remember that to get to the next symbol on the first tape, the Turing machine has to move k steps. The head is going to move by k steps. Okay? So I'm just going to move some stuff out of the way here. Okay. And secondly, now remember there are k heads. K heads. Right? There are k heads. And so these heads will be tracked by hatted symbols. Which means, remember, so you initially have this alphabet. Now I'm going to add these symbols, 2, 3, up to k, and technically I even have the space. Then I have 1, 2 to k, and the same with sigma. The same with the space. So this is my new alphabet. But I can go back and encode this into binary. Right? Again, now I encode into binary. So I can go back to 0, 1, except now each symbol has size, like log base 2 of k, or maybe like whatever, it's something like 2 times log base 2 of k, just to be on the safe side. Right, so I go back and encode everything into binary. So even though I'm going to talk about symbols being hatted or whatever, you can think of it as all binary, and all that means is the head needs to read these log k symbols to basically figure out what's going on. Okay? Okay, so now what does the tape look like at any point? So here's your tape. And there are going to be a few symbols that have hats. So there's going to be some symbol that has a hat 1, some that has a hat 2, and something else that has a hat 3. And the head is over here. Right? The head is over here. Okay, so any questions about this process? Any questions about this process? Okay. Now I'm going to sort of go back, and I'm going to say something here which we can discuss later on. I will say that this is a technical condition. This is called time constructable. What this means is simply T of n is a computable function that can be computed in less than T of n time. I'm just saying that the time, what the simulation is going to do is it's actually going to first compute what T of n is, and it's going to use that fact. And you can also do it without it, but it just makes life much easier.
I can quickly ask a question.
Yes.
Wouldn't the encoding of the hat symbols introduce a log k factor into the
original bound. Yeah, so there may be a log k factor over there. So we'll go back and maybe I may have to insert a log k. So I think that maybe in my notes what I had written was it's computable by a TM in ck tn squared time using a different alphabet.
Okay.
And then this is going to introduce a log k. You're right. I think it'll probably introduce a log k. So, okay, the question is at some point the Turing machine is at this, and the heads are over here. Now the Turing machine has to go and figure out where all the heads are. Because it only has one head. It's a single tape, a single head. And it has to figure out where all the heads are. It has to go and read those symbols and then transition accordingly. So this needs to go and find all the heads. If the Turing machine already knows what T of n is, then it can sweep T of n steps and then sort of come back. Right? And that's sort of what T of n is there to do. Okay, does that make sense? So this is just to help it sort of sweep back and forth. So what it can do is, because it knows that if the running time is T of n, then all the heads are going to be within T of n of each other. So now let me discuss what my machine M prime. So this is going to be the machine M prime that simulates M. So the first thing it does is M prime computes T of n. And again, you can get rid of this assumption, but it's just easier this way. And so then M prime goes out sort of minus T of n steps in the tape and puts a marker there. So that it could put another symbol. That's like the end of file. So it puts an end of file symbol at minus Tn, goes out minus Tn steps and plus Tn steps, and does the same thing. Right? And does the same thing. So it puts out markers. It knows that the heads are never going to go out of that region. So it goes and puts the markers there. Now, I'll say, to simulate a single step of M prime sweeps between the markers, or I should say the head of M prime sweeps between the markers, records the hatted symbols, stores in the state, makes the transition, then it sort of sweeps back to move the hatted symbols and rewrite whatever it has to do. So it has to move the hatted symbols according to the transition function and rewrite those symbols. Okay, does this make sense? So what it's going to do is it's going to go there to there. It's going to go all the way back. It's going to find whatever symbols there are, store them in the state, make a transition accordingly, and then it needs to go and move these heads either to the left or to the right, so it can store that in the state, and it needs to rewrite the symbol over there, which can also be stored in the state. So then it goes, the head will go back and make those changes. Okay, is this clear? Questions? so now we need to discuss the important question of how long does it take to simulate a single step of M? How long does it take to simulate a single step of M? Any thoughts? Any suggestions?
I would say about the approximately the amount of time, or approximately the distance that there is between the two markers times a constant.
Right, where that constant may depend on k.
Yeah.
Exactly.
You do one sweep in order to read all of them, and then you have to do another sweep to or maybe you don't have to sweep through all of it, but you would have to write the new positions of all the heads.
Right. So that, I mean, and potentially you could sweep back. So you realize that the problem, or these heads could be far apart. And so the Turing machine has to go back and find where those are. And therefore this simulation, it's something like, some constant k log k times t of n. Right? And k log k, because we are essentially encoding all of these things in log k bits, and it's k because there are k tapes, so we've spread things apart. So it's t of n, and there's some constant c because it has to sweep, it has to record these symbols, and it has to store in the state. There may be some operations over there. So that's what it takes to simulate a single step. And so the total running time is at most ck log k tn squared. And I should have, as was pointed out, I think I didn't put the log k over here, so I should probably just put the log k over here. So it's ck log k. This is not as important as this, so tn squared. Right? So the total running time is at most tn squared. So I just want to put these things together. It's a useful lemma that we have. And then I'll discuss this more. So I'll say if f is computable by a TM with arbitrary number of tapes, or I should say that, with some number of tapes. It's some number of tapes. So it's a Turing machine that has some number of tapes and some alphabet. By a Turing machine in t of n time. Then f is computable by a standard Turing machine in c t of n squared time, where c is a constant that depends on m. So I'll say the Turing machine is m. So what this is saying is this is a very important lemma, because what it says is it doesn't matter what the alphabet is, and it doesn't matter how many tapes there are, as long as you're okay with the quadratic factor. So it says up to the square factor in the running time, which can be a big deal. The model really doesn't matter, up to the square. And I'll just add at this point, though I don't think I'm going to actually prove this, because in some sense I think it's a very interesting proof, but so there's a theorem of Henny and Stearns, and this is in 66, which actually says the simulation can be done in C t of n log t of n. So you can actually do much better than the square. It's very clever because it actually doesn't have to go back and forth. It sort of introduces spaces in very clever ways. But I'm not going to go over that proof. Maybe I'll put some parts of it in the homework if it comes to that. But this is sort of the main simulation theorem that we are going to use, because what this allows us to say is we can, up to the square factor, we can just focus on standard Turing machines. Does the lemma make sense, and does the proof make sense? So please stop and ask me questions. I'll just quickly sort of sketch out what Henny and Stearns does. So what we did was we interleaved the tapes, but a different approach is to actually stack the tapes one on top of the other. So you could stack the tapes, and then you could treat this entire thing as one symbol. Does that make sense? So you could have the heads, you could have your hatted symbols here.
Oh, okay, I see.
But but even then this doesn't tell you how to do it, because your head has to go back and forth. So what you instead do is, instead of trying to move the heads, you actually move the tape and keep the head in one place. So you actually move the tape. So think of this as going to always be the position of the heads, but then you have to move the tapes back and forth. Now the problem is, when you need to move a tape back and forth, it seems like you have to shift all of these symbols. But what you do is you introduce gaps in various clever places so that the shifting is not going to be that expensive. It's quite intricate. I mean, it's a really beautiful theorem, and it's worth it's sort of worthwhile proving, but it ends up taking almost half a lecture, and we don't necessarily need the full power of Henny and Stearns for many of the arguments that we're going to discuss.
Of course. On a different note, earlier you noted that T of n has to be time constructible.
Yes.
Or rather, ultimately it has to be computable.
Right.
But because of the fact that the original, or isn't the time function kind of computable by definition, since you can just run the original, since the original Turing machine is computable itself. You run it and then you count how many steps it takes. I know that you can't. That would kind of be a little circular if you're simulating it, but then all you kind of need to do is first show that it is computable, and then you can use it in the proof to say.
Yeah, so the problem is, so technically T of n is only an upper bound on the runtime. It's not the exact running time of that. In general, when we refer to something running in T of n time, we're just saying T of n is an upper bound on the number of steps. And that's why I'm just being a little safe here. If that makes sense. It's some upper bound that is being provided.
But the number of steps that it takes to run the Turing machine will be definitely computable, and it will be no more than T of n as well.
That's true. That is true. But because I state the theorem with just saying there is some upper bound that is provided, I just want to make sure that that upper bound is computable. Again, you can, these are only for NASA. You can get around these things by other ways as well. And
right.
But you're right that you could say that you have to be careful. I mean, the process that you described doesn't give an efficient way of computing T of n, right? Because T of n is the maximum running time over all possible inputs of size n. And so then my simulation might take too long to compute T of n. So that's why you want something that computes T of n efficiently. And T of n itself, the exact running time might not be computable efficiently, but an upper bound might be computable efficiently.
See, so if we were being very technical about it, then would we also need to include the runtime of computing the amount of runtime we need?
Exactly, which is why I was careful here. That's why I said T of n is a computable function that can be computed in less than T of n time.
Okay, I see. Okay.
Yeah. So I put that in there just to make sure that all of this works. Yeah. But you're right. One has to be careful with that. Okay. So, given this discussion, a natural place that we come to is simulation of TMs, the universal Turing machine. Okay, so we are all used to universal Turing machines because, so we can think of, if M is a Turing machine, I'm going to use M prime for the encoding of that Turing machine as a binary string. Okay, it's just an encoding. And UTM is the universal Turing machine. So UTM takes as input, and I'll just say that, this is my symbol for the encoding of whatever is in there. So I'll just write something out and then hopefully it'll be clear. The universal Turing machine takes M on input, M and X. So given the code and given an input, the universal Turing machine runs M on X and produces the output. Right? So the universal Turing machine is a Turing machine, which is essentially a computer. Like, if you think of every single piece of code as a Turing machine, every single piece of code is a machine by itself, your computer takes the code, takes the input, runs it on that, and then gives you the output. So the universal Turing machine is essentially a mathematical abstraction of a computer, a general purpose computer. Any questions? Does that make sense? And so we can interpret the lemma that we have, and we can just say that if M is a T of n time Turing machine, then the universal Turing machine M of X, or we can design, or I'll say that. So first question before I go, is the universal Turing machine unique? Okay, let me poll you and ask you that. Oh, this is something.
What do you mean by unique?
Sorry, just give me 1 second. Let me fix. There it is. Sorry, it's something doesn't like something here. there exists a universal Turing machine, UTM, such that if M is a T of n time Turing machine, then universal Turing machine of Mx runs in C times T of n square time, where this is a constant depending on M. This is what we proved, and if you use Henny and Stearns, you'll get this. Right? So this would be by Henny and Stearns. So does this make sense? So now what we have done is we can give some sort of upper bound on the universal Turing machine, and we can say the universal Turing machine gives an efficient simulation. And that's why the Henny and Stearns theorem is also sometimes referred to as the efficient simulation theorem. One can think of it as actually it's a theorem about universal Turing machines. Okay? Any questions about that? Okay, so we will be revisiting, some of these things later on. But it's important that I'm just sort of brushing up this concept of the universal Turing machine.
I had a quick question.
Yes.
Maybe I'm forgetting something, but can the universal Turing machine take itself as an input?
Sure.
Is that a problem in any way? That's fine.
No. The universal Turing machine, if it took itself as an input, so it could take as input, it usually takes as input a pair. It takes a machine and an input for the machine. So it could take as input itself and maybe again itself. Maybe that'll run into an infinite loop. One is not, what you will probably get is that, if it took itself as input and this process halted, then you could start trying to get into contradiction. So actually, why don't we go ahead and, it was sort of something that I was thinking about anyway, that is to talk about the undecidability of the halting problem. And so maybe that'll clarify some of these things. But at this point, are there any questions about the universal Turing machine and the simulation lemma? Okay. So now I'm going to state sort of an important theorem. This is in effect, this is similar to the undecidability of the halting problem, but I'll do the undecidability of the universal language. So let's just say that we have the universal Turing machine. The language of the universal Turing machine. This is the language of the universal Turing machine. So the language of the universal Turing machine is essentially mx, where m accepts x. Right? That's what the language of the universal Turing machine is. And so the important theorem, and this is, in effect, this is Turing's theorem talked about halting. I'm going to talk about the universal language, and essentially, the proofs are fairly similar, is that this language is undecidable. Meaning, there does not exist a Turing machine that always halts, whose language is the universal, is L of UTM. Right, and this is exactly where one can do the classic diagonalization flipping proof. And so we'll say suppose not, suppose this was decidable by Turing machine M. Right, so suppose this was decidable by some Turing machine M. So what the Turing machine can do is it can take an input, it can take as input a machine and code. It can go ahead and decide, whether, well, actually, let's do it even directly, right? It takes as, okay, so let me just sort of say this. So suppose it was decidable by Turing machine M. So now let's construct. So I will call this as MU, and that's for universal. Construct M as follows. So M, and it's going to interpret the input itself as a machine that I will refer to as M prime. So sorry, there's a lot of M's over here. So suppose the universal language was decidable by some machine MU. I'm going to construct a new machine M as follows. I interpret the input as code. Okay, I interpret the input as code. Now the first step is using MU, decide if M prime accepts itself. Right? Decide if M prime accepts itself. And if so, reject, else accept. So this is now a well-defined Turing machine. Right? This is a piece of code that makes sense. So it interprets its input as code, and it will simply decide if its input code accepts its own code, if that machine accepts its own code. And it can decide this using the universal Turing machine, which we just argued would always halt. And if M prime accepts itself, then it rejects, otherwise it accepts. Does this make sense? And so now I'll say feed M to M, and watch the contradiction. Now I'll just end the proof right here. There's a contradiction. You should be able to see this. If not, go and look at it. You've written a piece of code. Now try to figure out what happens if M got itself as input. And you'll see that, you'll get a contradiction, because if M accepted itself, then this will say it rejects, and vice versa. And therefore, what this says is actually this machine mu cannot exist. Because this machine always halted, and that's why you even went to step 2. The proof of the halting theorem is also the undecidability of the halting problem is very similar to this. Okay, so I'm going to end here. This was sort of sketch of the proof, or this is the proof that the universal language is undecidable. So the important, steps to take away from today was really the simulation theorem. And we proved that you can simulate with a quadratic sort of loss in time, but you can actually just get Tn log Tn using Hennian-Stearns, but I did not discuss the proof of Hennian-Stearns. And using the universal language, this is the universal language here, and you can prove that the universal language is undecidable. So I'll end here, and I'll take any questions that you have.